Today is, I guess, 15, 2019. I have basically my senior assistant, Dr. R. We are not gonna actually name him completely because we are gonna have kind of out of the box approach toward gravity, and we don't want people to discredit his amazing work, previous work, because we want to say King is naked. The thing is, basically, we are going to work on a quantum traction theory because of three issues. I have also here, can I name you? Nanny, my junior assistant, and Christine, my junior assistant. Basically, they are physics enthusiasts like me. I am no scientist. Basically, what we do in this company, in our company, we learned how to think out of the box and how always think that basically existing laws and existing systems can be better. So there are basically four issues with gravity, which is a fundamental force. Okay, I'm gonna take back that word, force. All of the scientists, they use that word. I'm not going to use it. That we want to find a way to solve. There are three problems at this moment. One, galaxies, galaxy gravity, keeping it in motion. Yeah. Second issue is compatibility between quantum mechanics and general relativity. And third is about twin products and frameworks. Okay, so basically with the current general relativity we have three problems, and special relativity and general relativity. We cannot account for all of the gravity that keeps all of the galaxies in motion. We cannot match it with quantum physics, and we cannot solve twin paradox with a special relativity only. We should account gravity or acceleration in to solve the twin paradox. So what we are going to do is this. First, I'm going to actually talk about how general relativity addresses the gravity. Basically, general relativity addresses the gravity as a space-time curvature. So basically, it is kind of a wave in, for example, if this is the dense object, we have this situation addressed by general relativity as space-time curvature. This means this is basically how gravity works in general relativity. So, for sure, in many probes, this is kind of confirmed that basically space-time is changing, and there is a curvature there by massive object. Now, what we are actually trying to readdress here is this. Rather than massive object creating a space-time curvature, in quantum traction theory, we are gonna create, let's say at this moment we call them fabrica. Why I want to call them fabrica? Because this is a name that we can actually use later. First of all, this belongs to Georgia, this belongs to Tbilisi. And it is kind of like fabric and alpha together. And we can actually use it in formula later. Let's say, what if space, time, and gravity are the same thing. They are not causing each other, like they are not affecting each other, but they are exactly the same thing. Let me actually go very simple. Let's say these are fabricas of a space. Okay? These are not particles.
Medium.
Yeah, like not ether for sure. This is not ether, I will tell you why, because in ether we don't have time. In ether we never address time. And these are handling the time, space, and what is happening in gravity. Let's call massive object or mass consumer of fabrica. What that means? We have a massive object here, and constantly, this massive object eating up. I'm using very non-scientific terms, but there is a reason for that. Consuming these fabricas. Therefore, let's say this is massive object. Let's say Earth. Rather than curvature of a space-time, is eating up the space and time. Eating up the space constantly. So it doesn't create curvature exactly. Curvature is the result of eating up the space and time constantly. What this can solve? A lot of things. First of all, because these are basically we can actually call it kind of quantum system. We can address a lot of equations later with quantum physics in gravity. Second, the most important thing, these fabricas, they can actually be accounted as dark energy as well, because these are getting created constantly as well and eating up by mass constantly as well. Therefore, the whole expansion of universe, dark energy, means constantly creating these fabricas, and gravity by matter means eating up the same fabricas. So, what will be the difference between this definition of gravity and the definition that Albert Einstein has on GR? Okay, I'm going to tell you the problem now. Okay, immediately to the problem. How we can test this theory. Okay, we have a clock here, T1. This is center of Earth. Gravity is 0. Let's say we create a room here and we put a clock in the center of Earth. Okay, what will be the answer of GR for clock counted here? The answer of GR to this will be the clock, because there is no acceleration, there is no gravity in the center of Earth, there is no gravity by definition of GR. Why there is no gravity in the center of Earth? Because the curvature which is defined in GR is cancelled out in the middle of Earth, correct? So the slowest clock is here, the faster clock is here, and the faster clock is here. This is the fastest clock around Earth and inside Earth by GR. Am I right? Because G will be 0. Therefore, this is the fastest clock. But in quantum traction theory, which is like, it can be very easily tested, and the probe is not going to be that expensive, this is the slowest clock. It is even slower than here. they tested GR from the surface of Earth till here. They did that. They always looked at the sky, which is right. But they never tested any clock between, like, in the middle of, not middle of the Earth, but at least here maybe.
Thank you.
Yeah. And why? Because here we have more kind of, because mass is around it, they are eating up like faster, like the time, space, fabricas are getting disappear faster. And the faster they get disappear, the time will be slowed down more. Because just imagine, I have this room full of balloons. And what will happen if these balloons start to break? The other balloons from all around they come to me. But the thing is, the faster that like, because these are accounted for time and space itself, this actually will be the slowest clock in this story. Now, why this is important? Why this is extremely important? Because in galaxies, in general relativity, gravity can cancel each other, right? Let's say, this is extremely important. Let's say I have a star here.
Like forces can cancel.
Yes, and I have another star here. Here, I have zero gravity.
Okay, forces cancel.
Yeah. The curvature of a space-time, because it's like a wave, like let's say, it will get cancelled, it will be a straight line here. Correct? Because the gravity is zero.
At one point, forces cancel.
Yes. And here, we have the fastest clock, but it's not the case. Because this will eat up the space and time, this will eat up the space and time as well, and the time here, according to general relativity, is the fastest. For example, the observer is here. But according to QTT, this will be the slowest. Because from both sides, we are pulling the time and space. And this is called traction. I'm gonna use three terms: protraction, subtraction, and traction. So gravity is not a force, it's a traction. And that can account for this very small number that they cannot count in quantum physics because they count it always as a force. There is no force. This is traction and subtraction of the space and time, and subtraction of fabricas, that we are going to call it after fabrica. And this is going to address why galaxies, they have more gravity than is accounted for in general relativity. Because in general relativity, gravity can cancel each other. In this theory, in very, very large scale, like a galaxy, they are not canceling each other. They are, because let's say I have a room that I'm destroying the balloons here, and you have a room that you are destroying the balloons here, and another room. We will consume a lot of balloons. We are not canceling each other. In general relativity, it seems like that. I'm making the balloons, but there's no balloon. Basically, there's a curvature. It's like a wave. It's canceling each other. But in the traction theory, because all of us, we are destroying these small balloons, we are gonna actually accumulatively, we are gonna consume way more balloons. But in general relativity, no. So basically, it is not gonna get accounted between Sun and Earth. It's the small gamma that we are gonna add to the Lorentz transformation later is not going to account between Sun and Earth. The calculation will be right, not between Moon and Earth. Okay, the calculation. But when we are talking about millions and billions of massive objects, that gamma, which is the difference that we talked about, will be huge. and therefore the gravity will be totally different in the larger scale. Now, why this is important for the second thing? Okay. Basically, when we are talking about quantum physics, always entanglement is in picture, right? So, if we are talking about time and space fabricas, let's use this term, far, far away, a galaxy far, far away, long, long time ago. It is the term that they are using in Star Wars. Two fabricas can be entangled to each other in this place and this place, because we are talking about quantum physics now. Therefore, what will happen? The time between these two, in Lorentz transformation, if we are talking about the electromagnetic field, will be zero. In the point of view of a photon, the speed in infinite is infinite, right? Point of view of photon itself. Like, if I am a photon, I started 12 billion years ago, and I ended up here, in my eyes as an observer, I will have zero time for this space-time, like a space travel, in my point of view as a photon. You follow me? Let's say I'm a photon, okay? What I see? I moved through the whole universe like this, without even passing a second.
Yeah, no, time doesn't move.
Exactly. So therefore, if I'm transferring from here to here, time passed for me like a zero.
Change.
And if I transfer from here to an object even more near, the double slit thing that we saw, again, time for me like will be zero. Because I will entangle two points of space in a two different time. Two different time and two different space, but it will be entangled. And therefore, this will be the answer for the double slit as well. What that means? It seems we are looking at past, or we decide about past, or we change the past. But just imagine, this, let's say this is 1 light year, this is 12 billion year, 12 billion light year. That was about the space of different observers. Like, we had more space, but they didn't count the time in the time of as the entangle of the two fabricas here. Therefore, what will happen? In that case, transferring two entangled photons, one to here and one to here, will have same time in the eyes of the photon, because these 2 points in time and space are entangled. So a point, a fabrica, in the future or past, they can be entangled. Because this fabrica is a quantum basically definition. The space and time will be a different thing than what it is defined in general relativity. So we can account even that kind of test. We can easily calculate it. And therefore, we can actually calculate other things as well. Now, even we can talk about special relativity based on this. What is happening in a special relativity? Why? When I'm moving fast, the time slows down for me. What will happen? Basically, let's say I'm moving from here to here, and I have a cloud. What will happen? This means I'm passing more and more and more fabricas. But these fabricas, I'm not talking about the nature of fabrica, because we should discuss it, and first we should go to equation and then we can talk about it. But the thing is, if I'm passing more fabricas, I'm passing less time side of the fabrica and more space time of, I'm passing more fabricas but less in time sector of that. Therefore, the faster I move, I pass more fabricas, and when I pass more fabrica, I'm moving through the space dimension of that fabricas. Therefore, I will not have time to be passed by me because I'm passing more. Exactly the same concept talking about the gravity. When the fabrica is coming more to me and faster, I will feel the time less because it is going through a space. The fabrica is coming from a space to me all the time.
Like these are fabricas, yeah?
Yes, exactly.
Here come,
Yes, the more that we are passing it, the more we will have to experience the time. You know what I'm talking about? Let's say, for example, these small objects, like objects, shouldn't say objects, but anyway, the faster I move through this, the less time, the exact Lorentz transformation calculation can be accounted here. The less time I have to say hello to each one. And if I have less time to say hello to each one, it means they have less effect on me. What is their effect? Time.
changing time.
If I stay less here, I will experience the time less and less and less and less. The more I'm like passing it faster, the less I will experience the time. And also the less I will even experience the space. This means length contraction. Because I'm moving through one of these dimensions, and then basically the length contraction even can happen because I'm experiencing length. And at a certain point I will be very basically like the length contraction will affect. And that's why also we can actually talk about the general relativity a little bit here. That's why the more that I'm passing, the